be complete.
Thanks. Yes, exactly. Um, Let me start maybe emphasizing again that, okay, since some people joined after we talked before, I'm actually not a mathematician. I'm a theoretical computer scientist. So, preparing this talk was a little bit funny for me because actually I've never given a talk just to a math audience, and let's see where the difference is. Exactly. So the background was that we found this problem in an open problem survey, originally posed by Andrew Granville, which is, given a set of numbers, can you determine if this is a sumset? So can you write it in the form x equal to a plus a? And now we're really asking this from like a computational perspective. So we would like to, like the question is there an efficient algorithm which, given a set x, tests whether x is a sumset? Um, and Yeah, maybe let's before we talk about any like of our results, maybe let's talk about some trivial answers to this question. So, what are some trivial algorithms, right? The first trivial algorithm you can think of is something which runs in roughly exponential time to the n, which is you can just simply test all possible subsets of the interval from 0 to n, and test whether x is equal to a plus a in polynomial time. So that's pretty slow, but at least it's some algorithm. And you can improve it a tiny bit by doing this. So instead of enumerating all subsets, just enumerate all subsets for which, like all elements, only subsets of the elements satisfying that 2 times the elements is in our set. Because definitely these elements will have to be in the set, right? So you actually get an algorithm which runs in time exponential in the size of x. Okay, but other than that, basically nothing was known. So that's basically what Granville suggested. And I guess while not being super explicit, whenever in theoretical computer science we see such a question, we understand efficiently as, is there a polynomial time algorithm? So Granville's question can be understood as, is there an algorithm which runs in polynomial time, poly n, maybe even polynomial time in the size of a set x? Okay, now our result is basically, most likely the answer is no. Specifically, we get this. Sumset recognition is NP complete, which means that there is no poly n time algorithm if you believe this complexity assumption that P is not equal to NP. Maybe, okay, here, let me ask you something. So I'm assuming math people actually know a superset of what we do. So I'm kind of assuming all of you are familiar with NP hardness and all of this. But is that something which I should maybe like quickly summarize again? Like, what is NP hardness? What does it even mean? Or is everyone comfortable with that?
Not for my part.
Okay, so if there's no complaints, then I will basically not talk about NP hardness at all. We'll just assume everyone is completely familiar with that. Oh, by the way, but before I continue, let me remark one thing, and that is our result basically applies to, like in the paper, we specifically talk about integers and also some other groups, like for instance, finite field vector spaces. You could probably do it for like all finite groups, though you have to be a little bit careful on how to represent groups and like from a computational perspective. But in this talk, let's just focus on integers. Okay, good. So I'm going to skip this entire P versus NP stuff then and immediately jump to one prep slide, which I guess is necessary. Let me talk about the NP complete problem, which is 3-set. Okay, I promised to prove you like a theorem which says some problem is NP hard. So what we have to do is we have to show a reduction, to reduce some hard problem to sumset recognition. And the problem to always basically consider first is 3-set, the resatisfiability. So it's some work to just define it, but let me maybe just do it once to be on the same page. So this problem is defined like this. At the very basic level, let's consider them variables, x1 through xn, which can be assigned binary values 0, 1. We say that a literal is either a variable or the negation of a variable. So positive literal is a variable and negative literal is the negation of a variable, which are satisfied by an assignment in the natural way. So a literal is satisfied, a positive literal is satisfied if we set the variable to 1. A negative literal is satisfied if we set the variable to 0. then you can consider clauses. So a clause is the OR of three literals. And in particular, it's satisfied if at least one of the three literals is satisfied. And then finally, you have this 3CNF formula, which is short for three conjunctive normal form formula, which is just an end of many clauses. So it's satisfied if and only if all clauses are satisfied. Okay, that's a lot of buildup, but actually it's pretty easy. Like maybe just as a quick example, this formula, for instance, you can verify that if you set x1 to 0, x2 to 1, and x3 to 0, then all clauses are satisfied. I guess because of this literal, and this literal. But on the other hand, maybe this.
The input size is considered to be the number of variables, right?
Yeah, good question.
The length of the formula we don't care about for some reason,
Yes.
right?
Yes. Okay. I mean, you don't care about it a lot, but you can, if you want to, assume that it's just cubic size. Basically, because you can assume that no clause is repeating, and then you only have a cubic number of clauses which you could put in the input.
Okay.
Good. Okay, and then of course the three-step problem is you have to check whether a given 3CNF formula is satisfiable, in the sense that is there a satisfying assignment. And one of the very basic theorems in complexity theory was this Cook-Levin theorem, which says reset is NP complete in the sense that it captures NP computations. Like any program which runs on like a non-deterministic polynomial time Turing machine can be reduced to solving a three-set instance. Okay, again here, I've been very quick on this page. Maybe you could reassure me quickly that we're all on the same page about this. Awesome. So I've been absolutely correct. You just know a superset of what we know. Okay.
Well, we're less experts in the reductions and stuff.
Well, I mean, the NP hardness reductions typically are not too hard. Maybe, I mean, yeah. But actually, this one is also not technically hard, right? It's long, it's a little bit deep, like it's a little bit technical, but it's not deep. Okay, so this is our roadmap. I want to prove three lemmas in this talk, which, if you combine them, prove that sumset recognition is NP hard. Okay, so let me go through it maybe once. So suppose you're given a 3CNF formula, then the first lemma says that you can construct three sets. This is different than the original problem. You can construct three sets such that phi is satisfiable if and only if you satisfy this condition here. Okay, so it means if there is a set A, which is not unrestricted as before, but it's actually a subset of the set U, and which is not equal to, like, whose sumset is not equal to something, but whose sumset is sandwiched between two sets X and Y. Okay, the second statement then is that we can transform these sets U, X, and Y further into two different sets U prime and X prime, such that, you know, this condition from before is just equivalent to the statement that there exists some subset A prime, now subset of U prime, which is equal, like, whose sumset is equal to X prime though. So we've kind of made like a little bit more restrictive. And then the final step, we really reduce to the sumset recognition problem from before. Like you can, just given these sets U and X, or U prime and X prime from before, you can construct a final set X prime such that there was a solution before if and only if X prime is a subset.
And let me just make sure everyone's clear about one thing. You're only talking about the decision problem. It's just whether X can be represented as a sumset. And there's zero information about what the set A might look like. It's just a yes/no question.
Yes. Though, I mean, let me say, like, there's a very common result in, like, for NP complete problems, which is if you get a fast array algorithm, let's say the decision problem and the finding problem, they're typically equivalent. So here it's actually true as well. Like if you have a polynomial time algorithm for the decision problem, you can easily you should also easily get an algorithm which actually finds the set.
Is that a theorem or a heuristic?
Well, for SAT, like the typical thing is like you know, you try to force values one by one. Like let's say you force the first variable to be true and test whether it's still satisfiable. If so, this choice was correct. For subsets, probably it's a little bit more tricky, but I would imagine that still something easy works. I haven't checked though. Okay, so this is the roadmap. And you know, these steps might look a little bit alien, but actually there's three conceptual steps behind these. Maybe let's just believe this for now, focus on lemma 1, and then after we finish lemma 1, we can go into more details why you actually need these weird conditions that A be a subset of U and that the sumset is sandwiched between X and Y. Okay? So let's start. This is lemma 1, which we want to prove. So first step is the reduction from preset. And let's start with a easy warm up as like an observation. It's this. How would you encode variables? Right? This is always, whenever you design an NP hardness reduction, you have to take care of different parts, and one of them is you kind of have to encode different choices. And for sumsets, this is actually like for this particular problem, consider this extremely simple instance, right? Suppose that U is the set containing 0 and 1, X is empty, Y is the set with 0 and 2. Well, then it's almost trivial to verify that, this is exactly 3 solutions. You can either pick A to be the set containing 0, because then obviously this is a subset of U, and well, you satisfy this condition. You can also pick it to be 1 or empty, but you cannot pick it to be 0 and 1. Because in that case, A plus A would in particular also contain 1, but does not contain in Y. Okay, it's pretty trivial, but what does it mean for us? Well, it basically means you found a way to represent whether a variable is set to false. This would be if the set is 0. Whether a variable is true. This would be if the set is contained exactly 1. Well, and there's a third case, which is just we don't care about the variable. Like we want to say the formula would be satisfied. It doesn't matter either you set the variable to true or false. It would be satisfied either way. Okay, so this is maybe the baseline idea. This is what we call a variable gadget. Okay, this is like a super trivial, constant-sized way to encode a single variable. And now we'll build on that. Okay.
Wait.
Okay.
So I understand that you complexity guys talk about these gadgets for literals. But so how does this encode a variable? What does that mean?
Okay, let's say first, this is not a rigorous statement yet, right? I'm trying to build some intuition. But what you eventually, for all these empty hard problems, basically what you have is you have some search space. For satisfiability, this is the set of all assignments. For sumset recognitions, well, it's the set of all sets A. Oops, set of all sets A. And now you have to, in order to reduce from set to sumset recognition, you kind of have to map the search space from one problem to the search space in the other. So in particular, you have to be able to encode just a single variable decision. You have to be able to encode it somehow into our new problem. And a good exercise is always to start with just a single variable then. And this, well, just means here, like for some problems, it's not even possible to encode a single variable, basically. And here you can see there's a trivial construction. It doesn't mean anything yet, of course. It will mean something as soon as you can encode n variables and as soon as you can encode clauses. But we'll get there. Okay? Okay, so let's go on. Let's try to simulate n variables. What would you do? Maybe you would just think, well, we can copy. Like you can just take a variable gadget and you can copy it another time and just shift it away with some difference. This would be maybe the natural approach. But you have to be a little bit careful. So actually, the construction we would suggest is this. Let me start by saying this. Suppose that this set is the numbers S1 through Sn is a set of numbers without non-trivial solutions to this inequality or this bound, which if you think about it, is just the same as saying, this is like a 3AP free set multiplied by 2, let's say. Okay. Now consider the following instance. Consider the instance where
just a stupid. I mean, AP is arithmetic progression. Okay.
Oh yeah, arithmetic progression, exactly. Yes. Sorry. Sure. Good. So let's consider this instance now. Basically, what we did is we just copied the variable gadget from above a bunch of times, right? If you just look at U, we have done the same set, but we have shifted it around a bunch of times. And the same happens in our set Y. But we have to be a little bit careful because, if you consider sumset X, the sumset A, which satisfies that A plus A is a subset of Y, then in particular, the contributions from the same variable, like if you take the same variable, add it to itself, it will go here. But if you consider the contribution of two different variables, this will also have a contribution in the sumset. And for this reason, you have to have a different construction for these terms. Maybe let me jump ahead a little bit, and maybe then it gets clearer. So the claim is that the only solutions to this instance are the sets A, which look like this. So the set A is just, again, a union of all, like you have a bunch of shifts, Si, and at each shift, you either have the set containing 0, 1, or the empty set, but not the set which contains both 0 and 1. And again, we would interpret this now as saying, if this set AI is 0, would say, well, this encodes that the assignment of the ith variable is 0, or 1, or we don't care. Oops. Okay, now I claim that it's a little bit less obvious that this is true. So let me give you a quick proof. On the one hand, I claim it is pretty easy to see that this set A, like each such set A, indeed satisfies that A is a subset of U. That's pretty obvious just because, it's basically has the same shape, and obviously these three subsets are subsets of 0, 1. But I also claim that it satisfies the sandwich condition. The X part is trivial. And for the Y part, you really have to do what I was trying to do before intuitively. You have to consider all pairs of things, right? If you sum Si plus AI to itself, you will get to this part. If you sum Si plus AI to Sj plus Aj, you will get to these parts. And in both cases, you can see this is indeed a subset. And for this part, we need, again, basically that AI is either 0 or 1, but not both. Okay, but actually it's a little bit tricky because you cannot immediately say that it's not obvious to say that that we cannot pick AI being 0 or 1, like both the set containing 0 and 1, because it might just happen that this falls into this region. Right? It might just happen that AI plus AI, which contains 1, does not fall into this region, but into one of these regions. But actually, this doesn't happen. So, suppose that AI contains both 0 and 1, and suppose further that A plus A is a subset of Y. But then in particular, get that Si plus 0 plus Si plus 1, which just happens to be 2Si plus 1, is in the sumset and thus in Y. But this contradicts our initial assumption, because we said that, 2Si plus 1 would be contained in this, which in particular would be a solution to this inequality, which we ruled out in the very beginning. Okay, so what's the takeaway here? Well, if you can encode one variable, you can encode n variables by just copying these gadgets around. You just have to be careful with the placement so that the cross terms of two variables do not interfere with the actual variables.
How large does this actually have to be? You have some sense for it?
Good. So you could use a 3AP free set, maybe using variance construction, right? So then
Sorry,
you
what?
only the question is basically how large can you get? How small can the SIs be, right?
Right.
And for this, you could use variance construction for 3AP free sets, and then you would, if you start right with like n variables, you could encode them into universe which has size n times through the root log n. So very small.
Okay.
But it will get more costly later on. Like the variables themselves are cheap, but as soon as we introduce clauses, actually it gets more costly. Okay, but we're on the same page. This only encodes variables so far, but it does actually have this mapping I claimed before, right? It maps the search space from before into the search space of our problem now. Now what we have to enforce, this is always the next step, is as soon as you can preserve the search space, basically, you have to be able to enforce like satisfying assignments, like, right? You have to be able to enforce the constraints of your problem. So we have to deal with clauses. Okay, question at this point? Good, now let's continue. So here's the full construction. It gets a little bit more tricky. Let's suppose, again, that you get a set of shifts. Before we had these SIs, which were responsible for the variables. Now we also have these TIs, which will be responsible for the clauses. And let's suppose this is a set without non-trivial solutions to this more complicated expression here. Now correct me if I'm wrong, but I guess
Scroll, please. I can't see it.
Oh, I see. Okay. Well, then just ignore everything below. Like just focus on this for a second. Okay. Now I think in like additive combinatorics terms, in particular, what you could do to get such a set is you could take a B3 set, which I guess is a set which disqualifies all, linear equations where you have three terms on one side and three terms on the other side. And you scale it again by some number to deal with this condition that also, they shouldn't be equal up to some small difference. Okay, so this is our set of sets of shifts we pick, and then consider this complicated construction. It's kind of a mouthful, so let me maybe go through it slowly. I really tried a lot to, make it nicer on the slides, but I really couldn't. It basically needs some complexity, let's say. Okay, so what's happening? Recall from the instance before that the variables were encoded as sum shifts plus 0, 1. This is exactly the same here. And also in Y, you still have exactly the same terms as before. So what's new? What new is all these these purple terms. And they're chosen like this. So basically you have in U, meaning in the superset of the set A, which we allow, you also allow to include the following sets. Which maybe just let me spell it out once, which means you for each class K, and for each variable which appears in the class, let's say positively, you also include the number tk minus si minus 1. And for each variable which appears negatively, you add tk minus si. Okay, now why is this a good idea? Let me maybe jump to the soundness proof and hopefully it gets clear. Well, suppose you have a satisfying assignment to the three-set formula. And suppose you pick this set A. Okay, so for you, the ith variable is set to alpha I, so you include the point si plus alpha I. And also you include all the terms in the set ck. Then what happens? Then I claim that this is actually a solution. Okay, let's see. I claim it's easy to verify that A is a subset of U and that A plus A is a subset of Y. Let's check again. A being a subset of U is indeed easy, right? Because we checked like alpha I is 0, 1. So definitely this part, this is subsets. These are even equal. Good. I also claim that it's easy to verify that A plus I is a subset of Y. That's some casework, but okay, let's, this term plus this term goes here. This term plus this term goes here. And this term plus this term goes here. It's easy so far, just maybe a little bit much to read. The interesting part is I claim now to think about X. So how do we prove that X is actually a subset of A plus A? For this, recall that focus on some clause, say the kth clause. And the kth clause is definitely satisfied by alpha because alpha satisfies all clauses. So there's really just two choices, right? Either the clause is satisfied by some positive literal. So there's a positive literal xi in the clause such that alpha I is equal to 1. But then notice that, si plus alpha, si plus 1 is in the set, but also tk minus si minus 1 is in the set. And they add up to tk. Now, let me scroll up again, just as a reminder. X just consists of the values t1 through tm. So we have, in particular, we found all clauses. Like for each clause, we want to argue that tk is in the set, A plus A.
Just 1 second. The alpha represents a substitution for all the variables, true and false.
Exactly.
And
Yes.
alpha I is the choice made for the ith variable.
Exactly. Sorry. Yes.
Okay,
Maybe I should have clarified. Exactly.
Thank
This is what we typically call an assignment. Exactly. Good. Exactly. And let me also go through the symmetric case, right? Maybe the kth clause is not satisfied by a positive literal. In this case, it would be satisfied by a negative literal. But then you have that, well, si plus 0 is in the set, but also tk minus sa, and they also add up to tk. Okay, in other words, we have constructed this instance exactly in such a way that whenever a clause is satisfied, some contribution here and some contribution here add up to tk. Okay, good. So this proves the soundness. Definitely every satisfying assignment leads to a set which satisfies the conditions we need. Now, the completest direction says that whenever you have a set satisfying these conditions, you can extract a satisfying assignment. Now, the argument is basically the same as before, but you have to be careful that there's no spurious solutions. Now, I don't want to go into many more details, but let me maybe just show you one problem. This is the problem from before, right? If it could happen that S2Si plus 1 falls into this range, well, then you could simultaneously set a variable to be 0 and 1 at the same time. And this is obviously not allowed. But we cannot have this due to the condition we imposed before on the shifts. So this would be a contradiction. But there are some other bad cases. Like, for instance, this one. Now, maybe you could also set like this variable, like you still have to enforce that the variable is not 0 and 1 simultaneously. This could also fall into another region of the set Y, maybe this region. So this leads to another set of, actually it's this one. This leads to another set of equations which you have to rule out. Maybe let me just show you all the errors.
So these are all the cases that you need to sort of make sure don't happen.
Exactly. These are all the
Case
cases
analysis for the various things that could fall into the wrong set.
Exactly. I don't want to go through all of them. Yes.
No, but basically for each one, you can rule it out on the basis of the conditions we imposed at the beginning.
Exactly.
Okay.
In a very stupid way, right? We just say, well, the TIs and SIs, they are as if you chose them at random from a large set. So there's just no interference between them. Exactly. Maybe very quick comment is at the very end, like there's two things which could go wrong, right? We have to make sure these three to say that the variables cannot take simultaneously values 0 and 1. And this means that we don't just claim a clause is satisfied while it's actually not satisfied. But okay, these 5 cases really are exhaustive. If you can rule these out, then the completeness proof is exactly the same. You just argue that each set, the set must look like this basically, well, or empty for a variable, in which case you don't care, and then you can extract the sound. I'm being a little bit hand wavy here just because I think it doesn't make sense to go into details. Let me know if you have questions though.
It's case checking. I mean, it's the same basic idea each time, just for a different configuration. Good.
I was told math people care about details, so I didn't want to be.
Well, I care. I mean, I care about them in the sense that I want to know that you check them, but I don't want to hear you checking them live.
Good. Okay, so let me then let's consider this proven. Let me talk a little bit philosophically. Why did we need these conditions A be a subset of U and A plus A being sandwiched between X and Y? Like, what's the idea behind these? So let's first focus on the sandwich condition. If you think about it, this is really necessary to mask the positions in Y without X, right? So we say that the sumset A plus A is equal to X or Y up to these positions where we just don't care, right? So where did we use this in the reduction? Well, the critical part, for instance, is we made sure that a clause is satisfied if and only if all, like let's say the kth clause is satisfied, if this value tk appears in the sumset. But a clause, while it might be satisfied, it might be satisfied in, like, let's say, like it might be not satisfied by several other literals. So it might happen that a clause is satisfied by some variable, so tk appears, but tk plus 1 or tk minus 1 might also appear. Just because, maybe the ith variable does not satisfy the clause, but it appears positively, then you get a minus 1. So tk minus 1 is also in your set. But since we cannot enforce that this is the case or not the case, we simply don't know, or we don't want to know in advance, you have to be very flexible around these tk values. And we would like to just not care about these. And the sandwich condition makes us not care about these values. Okay, makes sense? there's some other subtle places where we use them. For instance, another important point is, well, we have all these cross terms here. Like let's say, you put alpha, like let's say the cross term alpha I plus alpha j. We don't know what this is. We need it to be a subset of like 0, 1, and 2. This is fine, but we cannot enforce it to be exactly equal to 0, 1, or 2, because it would mean that we force certain like cross terms to be like we would correlate some variables with this. So it's very important for us to not be too precise about some elements in the sumset yet. Okay. The other point is that we enforce that A is a subset of U, and that's essentially only there to say that there are no completely random points in your set. So whenever we had the analysis, well, we wanted to impose some structure in A in order to say that, for the soundness argument, it doesn't matter. For the completeness argument, we want to say, well, A at least roughly looks like this. And there's no like complete random points in there. So this is just very basic that we need the statement that A be a subset of U. Okay. But these two can also be fixed with two very, let's say, two different ideas. And this is exactly what these lemmas 2 and 3 will now do, right? So first we will get rid of the sandwich condition, and then we will get rid of this A being a subset of U condition. Unless there's any other questions, let me move on. So the second part would be exactly to deal with the sandwich condition, which means to mask some points, and like loosely speaking. The lemma we'd like to prove is this one. Now, given these sets we have constructed in the previous step, before I assume they're between 0 and n, maybe let me just now, for this part of the proof, assume they're between 0 and 2n, a little bit more convenient. Our goal is to construct sets u prime and x prime, such that there is a subset, like an A, which satisfies the two conditions from before, if and only if now there is an A prime, which is a subset of U prime, and which satisfies that X prime is equal to A prime plus A prime. So there's no sandwich condition anymore. That's the point. Turns out this proof is a little bit technical. But what I want to show you is I want to give you the proof, or at least a picture of the proof, under some simplified assumptions. So maybe the most severe assumption is, let's assume there's really a single element in Y without X. So of course, there are many more. Basically, for every clause, for every cross term, you have a lot of variables, a lot of things which you want to mask now. Let's suppose there's just a single one. Let's also suppose that this element is even. This is actually without loss of generality. You can just multiply everything by 2, then it's even. And let's suppose that in the set X, the minimum value is 0 and the maximum value is 2n. Also, this can be easily enforced. The reason why we need this and why we will use it in a bit is because it implies that for any solution, the minimum of A must be 0 and the maximum of A must be n. Otherwise, you can never enforce that, A is a subset of, like X is a subset of A plus A and a subset of Y for which the maximum also was at most 2n. Okay, makes sense? So I'm going to give you a picture. The picture is not correct yet, but we'll get there. So let me write capital N to denote 2n plus 1. So just some large enough number, doesn't matter too much. And consider the following construction. Okay, it's just a picture, but let me explain it. So, okay. When I define the set A prime, obviously the set A prime, I don't want to construct in the lemma statement. The lemma statement just asked me to construct U prime and X prime. So this set A prime is just the intended set A prime, the intended solution which corresponds to A here. Now in this intended solution, A prime, I want to place A in the middle, in the sense that, I place it between 0 and n, capital N, exactly in the way that there will be no overlap with the parts I put to the right and left. Then to the left of it, I put the set, which is just a singleton consistent of z half, and the same here. Now, in the set U prime, I mirror the same construction, except that in the middle I put U. I still have c half here and c half here. What does that mean? If I now consider the sumset A prime plus A prime, how should it look like? Well, I claim it should basically look like this set X prime, right? Why? Well, in the middle, you have that A plus A. Like, now we have to do some casework. What is A plus A? It will land here. But also Z half plus Z half will land here. Right? So in particular, what you have here is that you have that, maybe let me write it somewhere. In particular, I claim that this is indeed equal to Y because you have that, A plus A union Z, which we can assume is, well, is Y, because this is superset of X. And C is Y without X. Okay. So the idea is basically that A plus A is exactly what we want, but we also want to mask the point which is missing in A, and we will mask it just by putting it there for another reason, by just putting it, because of these Z half contributions. But this approach leads to an issue, and the issue is this. Well, okay, there are more terms than just the one which we care about, more than just the Y, right? There are the terms when you add Z half plus Z half, which lead to Z and Z here. They're fine because they're predictable, right? The important thing is we have to construct X prime to be independent of the actual value of A. These values are independent of A, so they're fine. The real issue is these values here, the contribution of adding A plus Z half. Because this would force you to hard code a specific set A in the set X prime. Okay, does that make sense? So the construction we have so far, it has a good idea in the sense that it helps us mask a single element in Y without X, but it introduces the new problem that we cannot actually predict the outcome of the cross terms. Sorry, you wanted to say something, Moshe?
Not really. I mean, so you're going to need to somehow absorb all the alternatives from different possible A's?
Exactly.
Okay.
Well, absorb as in we want to put like some superset on top of it, which just masks everything, right?
Yes, which will cover.
Exactly.
And
That's exactly the idea.
Solving problems for one particular element. So you'd sort of imagine iterating this procedure for each element?
Unfortunately not. Like if you iterate it, it becomes too expensive.
Too big, yeah? Okay.
Yes. Actually, you have to do it in one shot. So you, instead of just, adding Z half there, you have to do like Z1 half, Z2 half, and all of them simultaneously. I just decided for the purpose of this talk, it's like a huge...
Easier to explain with one element.
Exactly. Okay. It's just easier, and I hope that you trust me that it will generalize easily. Okay, but let me talk about this masking, because this introduces some more problems, right? So maybe one point to mask this would be to introduce these two sets. Okay, so maybe in A now we introduce two more contributions, right? We put, by this picture here, always I mean like this half interval, meaning the numbers between all numbers between 0 and n. Then if we put them in the right place, so this would be a minus 3n, this would be a 2n, they would cancel this and would just put the entire interval there. Right? So that's great, because we don't have to worry about this point anymore, but now we have new problems. In particular, one term you introduce is the term when you add this to A. Right? So actually what you also introduce would be a block here, which has the form, well, this half interval, so 0 to n plus A. But the good news is, if you consider the simplifying assumption from before, right, that the minimum of A is 0, the maximum of A is n, then this set just happens to be all numbers between 0 and 2n. So actually it became predictable. It's not hard, of course, but you have to be very careful with the details here. Okay, makes sense. So maybe let me skip all the other stuff and just show you the final construction. Oh no, what happened?
Got tossed out of the slides.
I think I pushed my iPad in my computer and pressed the off button. Okay, be right back. Good. This is the final construction. So you have to add a lot more masks basically, but if you add enough masks, it will work. Okay, so basically, if you add enough masks, then you also have to take care of these terms. Then you get maybe this, but it's also predictable.
These are the actual numbers, the -6n to 8n, or that's just for illustrative purposes?
No, they are the correct numbers for a single element to mask.
Okay. And for a set,
Yes.
you'd need a few more?
Yes, exactly. If you want to hide or mask n elements, turns out you have to go up to like n squared.
Okay. That's
But
your polynomial.
It is a polynomial loss, but actually, I think if you I'm trying to present it in a modular way, but if you merge this step with the previous reduction with 3-set, you can get rid of the n again. So this is actually not the lossy step in the end. At the very end, let me comment about where you actually lose stuff. Okay. Good. I don't really want to go into more details here. I hope just the intuition got clear. I have some more interesting stuff to say in the third step. So should I move on?
Yes.
Yes.
Good. So last step, this is what we call positioning. Positioning in the sense that you can position the solution at a specific location. Okay, which was, we're given the sets U and X from before, and you want to make sure that there was a solution before, if and only if really the newly constructed X prime, set X prime is a sumset. Let me jump into the construction immediately, skipping something for the moment. So this is actually, basically the entire construction now. Now I'm not making too many simplifying assumptions. Think of the sets as follows. So A prime is again the intended solution.
Just 1 second. I think I may have lost track of what we're trying to do at this point. We've gotten rid of our sandwich condition, right?
Exactly.
And so what do we need to do now? What's our next step?
The next thing is we still have this condition that A be a subset of a prescribed set U.
Yeah.
And in the original problem, we just want to take an arbitrary unrestricted set.
You're trying to get rid of that containment of A and U?
Exactly. This is what we do in the final step.
I got it.
Okay, this is what I meant before with like positioning, right? U positions the set at some specific location. It enforces a superset, but now I want to say you can do it without the superset condition. Good. And the construction is this. So you're given these sets U and X from before, and we want to construct just a single set X prime such this is true. Now, when I write A prime here, I again mean like the intended solution here if A was the solution on the left. And now it's a little bit tricky, but the idea is this. I try to color code it a little bit, so maybe it's easier to follow. So suppose you're given some positions A, U, and S. 3 numbers, I'll tell you in a bit how to choose them. But for now, just think of them as some numbers. Now then in A prime, we construct it in such a way that at position A, we put the set A. And at position U, we put the set U.
Yeah, it's big U and little u, right? I mean,
yes.
Okay, fine.
Exactly. The number is little u, the set is big U, exactly. And at positions S minus U and S minus A, we put the singleton set containing 0. Now, let's have a look at the sumset of this, like A prime plus A prime. How does it look like? A with itself will lead to the term X, because we know that A plus A is equal to X, and it will be at position 2A, of course. Let's focus on this term next. This term sum to itself.
Sorry to again interfere, but
no worries at all.
When you write little a, you're sort of adding it to big A. I mean, you're shifting. That's what you're doing here.
Yes, exactly. So I want to say
it's a plus would have been called for, I think, or something. To show that you're shifting.
I see. Okay.
All right.
Okay.
As long as we know what we're doing.
Sounds good. Okay. Right, but okay. So this is basically the union of the set A shifted plus A, U shifted plus U, and so on. Good. Now then, in the sumset, you have that in particular a plus a is shifted by 2a. Good. Let's focus on this next. If you sum this to itself, it is still the set which just contains 0, and it ends up at position 2s minus 2u. This set, still the set containing 0, ends up at position 2s minus 2a, same thing. Now, the crucial thing which is about to happen happens at position s. Because what is going on? If you add this term plus this term, you just get the set a plus the set containing 0 is just the set a, at position, well, a plus s minus a is position s. But on the other hand, you also add u plus the set containing only 0, so you get u at position u plus s minus u, which also ends up being s. Okay, so these two contributions, basically s and u, end up at the same place in the sumset. And that's good for us because we want to enforce that the sumset there just be equal to u. That is, of course, satisfied by this term. And it is only satisfied by this term if a is a subset of u. Okay? So this is the key idea of this entire thing. Unfortunately, there is again these stupid cross terms, but this time they're actually harder to deal with, right? Because like, okay, which type of cross terms are there? Well, maybe you have a plus u at some position, small a plus small u. And we don't really know how to deal with this. So instead, what we will introduce again is these masks, right? So again, maybe let's put the set is the set of all elements between 0 and n here. And in the x prime, we also have these, which is the set of from 0 to 2n. But now I really should tell you what is these positions. And for these positions, we need a lemma. Actually, a definition first. So let me call a set a it's not our set from before. Just let me call a set a primitive if it satisfies this condition. So whenever you can write a plus a differently as a sumset b plus b, then a and b must be the same. Okay, inspired by like factoring notation. So what we need is this lemma, which is like which gives us a skeleton set. It's a little bit hard to read, but let's go through it slowly and maybe it gets there. So the lemma states this: there are three distinct integers, a, u, and s. This is the integers we have used the entire time. And these sets, so s prime is some other set of numbers. S is the union of the elements a, u, s minus a, and s minus u. So exactly the relevant positions here. Sorry, the relevant positions here. And the numbers in s prime. Now, we will use these numbers exactly as follows, right? At position A, we have put our, like at these 4 positions, we have put the sets from before. At the positions from S prime, we will put these masks. And in the set X prime, we will do exactly the same, but we will put the masks at, 2a, s, 2s minus a, 2s minus a, sorry, 2s minus u, 2s minus a, and all elements in S plus S prime. Okay. Now here's 2 conditions, which will make sure that this construction makes sense. The first one is that the set S is primitive. So if you like, what does it mean? If you zoom out, like just view the set from far away, then and just replace each of these blocks by an element if it's non-empty and no element if it's empty. Then the set A prime basically looks like S. Right? Because you have added only like sets at the positions in S. Okay? And the set X prime basically looks like S plus S. At least this is what the second condition here is claiming. Second condition says S plus S can be written as the set of 4 interesting positions, these 4, plus these sets, plus these positions, big S plus S prime. Okay, so what I claim to have established is, okay, this is like a skeleton for a construction in the sense that if you look from far away, A prime looks like S, and X prime looks like S plus S. Now, the additional constraint is that S is primitive, which means if you try to express X prime as a sumset, the only way, at least if you look from far away, is to use the elements in S. Okay? Maybe let me be a little bit more formal. I claim soundness. Okay, so if you have these sets A prime and X prime, in particular, you have that X prime is equal to A prime plus A prime. It involves a lot of casework, but the relevant cases we have already talked about before. In particular, that for this term you have A plus 0 union U plus 0, which turns out to be equal to U since A is a subset of U. For all the other cases, there's these masks which you have to take into account. But this is really not the point of the reduction. So soundness should be clear, I hope. Let's talk about the completeness. So I want to argue that whenever you have another set B prime, which can be written which happens to be X prime equal to B prime plus B prime, then we can infer a set A as claimed, like in the set A, which is a subset of U and which satisfies that A plus A is equal to X. Okay, suppose you have such a set B prime. Then since S is a primitive set, that is zooming out, I claimed before, B prime must look like this. It must basically look like A prime. At least from zoomed out. The specific sets here might be different. Let me call them B subscript A, B subscript U, and so on. Okay, does that step make sense? I'm hiding some details, but kind of just applying that S is primitive here. Okay. Let me assume. Okay, good. Okay, if you know that B prime really looks like that, then now there's 3 steps. First of all, if B prime looks like this, well, then I claim that BA plus BA must be equal to X. Why is that? Well, obviously BA, if you add it to itself, will end up at position 2A. So in particular, BA plus BA must be a subset of X. But I claim it must actually be equal to X because there's no other term in B which ends up at this position 2A. And that's really, again, using position property 2 from the lemma above, which says in the sumset, 2A can be uniquely expressed with these elements here. Like it's, 2A is disjoint from all the other contributions with S prime. Okay? Okay, so the first observation is that BA plus BA is equal to X. The second step would be to say the same thing holds for the set BS minus A. Because again, obviously BSA, if you add it to itself, will end up here. This set is the singleton consisting of 0. And this condition again implies that there is no other term which falls into the same position. Okay? But of course, if a sumset is the set consisting of 0, then the set itself must be the set consisting of 0. So now finally, observe that if you now add these 2 terms, this plus this, well, clearly they're going to fall into position S, but S is exactly U, so you get that BA plus BS minus A is a subset of U. Using this from before, you get that BA is a subset of U. Okay, so all in all, you have shown that BA is exactly as claimed. If you pick A to be BA, then its sumset is equal to X, and it's a subset of U. Okay, I feel like I lost a lot of people here. Maybe should I repeat something?
I keep going.
Yeah,
Okay.
I mean, it's just a lot. It's not, I can't see anything in particular that's, uh,
No, I agree.
problematic here. It's just, I mean,
Exactly. No,
my own ability to pick things up, was sort of quitting by this stage.
I'm sorry. I'm so sorry. Yeah, I know. I try to simplify things a little bit, but this really is the simplest construction we could come up with. Okay, let me finally tell you a little bit about the skeleton set. I'll be quick. Actually, what's the
The skeleton set is the only place where you're really doing something new in additive combinatorics, right? This is really an additive, I mean, this is really a new construction in sumset theory. Everything
I
else
guess
you were just building out, easy things in sumset theory and translating it for the algorithmic purposes. You really got some new sumset construction.
I would even argue though that this new subset construction is also pretty easy, right? Like all of these are just simple set constructions in the end. But okay,
I
let's
don't
talk about that.
recall ever seeing anything quite like your skeleton set before, so I
Okay,
would guess that it's a bit new.
okay, cool. Well, then let's talk about it. Okay, so at this point, forget everything about the construction, and the only goal is to prove this lemma. Okay, it's maybe not clear why you exactly need this, but let's prove it. And this you do in 2 steps. Okay, so first step is how do you even construct any primitive set? And the answer is it's extremely simple. You just take an arbitrary set, let's say between 0 and n. And if you now add 4n to the set, it becomes primitive. Okay, extremely quick, easy proof. So suppose that the set where we added 4n, I'm calling it A star, can be written in the form A star plus A star equals B star plus B star. So what we want to prove is that A star and B star are the same. Now, consider the following picture. So A star is this set which is something arbitrary between 0 and n and has a single element at 4n. So how does A star plus A star look like? Well, it has something arbitrary between 0 and 2n, something arbitrary between 4n and 5n, and a single element at 8n. And since we assume that A star plus A star is the same as B star plus B star, this is the same as, this is also how B star plus B star looks. Good, so it follows immediately that B star must be a subset of 0 to 4n, and also that 4n must be in B star. And that's basically just because, how else would you be able to represent the maximum element? Okay, next. But if 4n is NB, then I claim that none of the numbers which are strictly between n and 4n can be in B star. Because if they were, in particular in the sum set, you would get some numbers which are strictly between 5n and 8n. But okay, in the sum set, these elements are not present, so they cannot be in the set. So then just call the first n elements in B star, call this B, and observe that since 4n is in the set, you in particular have that these must collide with A in the subset. So they must be equal to A. Okay, so then B star is just the same as A star.
Yep.
Okay, so constructing primitive elements is actually extremely simple just by adding a large number. There's something interesting going on here for finite fields actually, but not for integers in the sense that, obviously for finite fields, you cannot just, same question, how do you make a set primitive? You cannot just add a large number. So what you could do instead is like open up maybe a new dimension. Like you have your set as an fp to the d, and you just add a d plus first dimension and you go in some step in there. Turns out the set does not become primitive this way, but you have to do it with 2 dimensions. Some reason, then it works. Anyways, okay, this is a way to get a primitive set. Now, how do you prove the skeleton set? Yeah, the construction is a little bit, it's a mouthful. Okay, but maybe follow. Let me just read out some parts. So let me call S prime to be this colorful part. How do we choose these elements? Well, we will pick them as follows. We will pick them, and in addition, these values J1 through J5 to be the powers of 5, first 8 powers of 5. Okay, so I defined A, U, and S, and additionally these 5 numbers. Now, let me call all elements in the sumset S prime plus S prime without these interesting colorful ones, I. So this is the ones, this is in the reduction from before, this is exactly the set of positions which we want to mask. This is the set of uninteresting positions which annoy us. Now, on the one hand, it's easy to count that S prime plus S prime has size 9, just in case work. But from this, it follows that the size of I is 5. Okay, and now write I in an arbitrary way as 5 numbers, I1 through I5. And pick the set S prime to be this. Let me go through it. So it's for every element, you have I1 minus J1, and then separately J1. So that if they would add up, if you sum them up, you get I1. Simultaneous, same for all the others, I5 minus J5 and J5. And then at the very end, you add this value, which is 4 times 5 to the 8. Okay. Why does that make any sense? Well, the first bullet, the first claim was S is primitive. And that's actually extremely straightforward now, because, well, the only thing you have to verify is that all the elements in S are between 0 to 5 to the 8. Well, there are some, sums of numbers which are at most 5 to the 7. Let's say there's at most 4 of them, so definitely at most 5 to the 8. And you have this additional element which is 4 times 5 to the 8. So the previous lemma just tells us the set must be primitive. Okay. And the second property would be to say that you have this weird union. Well, and this is just some calculation, S plus S. Well, it's all the sums which can be expressed using at least one contribution from S prime or no contribution from S prime at all. So it's like S prime plus S prime or the others. But S prime plus S prime, I can simply write as these elements and I. But for I have the property that every such element can be expressed as some element from S prime plus another element from S prime. So in particular, this is a subset of S plus S prime. Okay, and the final thing would be to say that this union is actually disjoint. This was the important part to say that actually, the position 2A can only be expressed as A plus A and no other way in the sumset. And this is actually where this weird construction with the powers of 5 comes into play. Namely, to see that there's no spurious sums which overlap, right? We have just observed that if 2A would be equal to some sum in here, then in particular this would correspond to an equation where you have on both sides at most 4 times each of these values, J1 through J5, A, U, and S. But these values are chosen exactly in such a way that every, sub-multiset of this with multiplicity at most 4. Okay, so meaning you can take every value up to 4 times. These all sum to unique values, obviously. So now if you go through all the, I'm being a little bit light in some of the cases, but then you can easily check that these are actually disjoint. Okay, that's it. That's the complete proof. I have some open questions for you. Maybe let me get you back with the open questions.
First, our speaker. Let me just make one quick comment, because you had said at the beginning you had never given a math talk before. But looking at your talk and looking at your paper, I would say it's all math. I mean, there's no computer science in there. I mean, I always thought complexity is just a subfield of mathematics to begin with. But you're going from 3-sat Boolean expressions to the construction of these sets, and you're doing, basically number theory. The only thing you're being careful about is you never have to do things that are more polynomial and expressions. But it's, it's just basically what you might call additive combinatorics or combinatorial and additive number theory. And it's great,
Nice.
and in fact, what I thought was funny was I tried to find your paper on archive. So I typed in your name and it said basically you don't exist. And I couldn't figure out why until I realized I was searching in mathematics. And then
Sure,
I
I
went
see.
to computer science and I put your name in, and there you are. But it's like
Interesting.
yeah, like an arbitrary distinction somehow. But
Okay, maybe now that you mentioned it, maybe we should have just put this also into a math category. I didn't even think about it at the time.
yeah, I mean,
Yeah.
whatever. But I just found I was like really, and I also went to math reviews, MathSciNet, and I couldn't find you there either. But
Yeah, it's weird. It's really disjointed, right? I mean, also, as far as I understand, you care about journals in the end, right? So even if you were to look up some statistics or something, I guess we would have completely different measures in the end. Anyways, maybe let me quickly tell you some open questions about this. One, which I hope you really find exciting, and maybe some of you can think about it because I'm not able to solve it, but I think it's actually somewhat fundamental. Okay, there's some lightweight follow-up questions. Is it still NP complete to solve the version where you not express it as the sum set A plus A, but A plus B, two different sets? This only really makes sense if you enforce that the two sumsets have size at least 2. The answer is probably yes. We didn't check all the details, but this should probably follow. So maybe the first follow-up question should easily follow from what we've done. We just haven't written it up. Maybe we'll do that at some point. I'm not sure. The next open question would be, what if it's A plus A plus A? And there it's less clear. I don't see any reason why this should be an easier problem, but at least it doesn't follow from, doesn't follow immediately. There's more work to be done here. Okay, these are maybe 2 open questions which are somewhat interesting. What I really care about is question 3. What's the true time complexity of sumset recognition? Like, what really is the fastest algorithm? What's its running time? We said it's not polynomial. Fine. Probably it's exponential, but what exactly does that mean? Like, what exactly is the running time? Our proof shows that it's...
Do you know it's not polynomial?
Well, assuming P not equal to NP.
Oh, yeah, right. So you don't know,
course.
you just...
No. We don't know. Of course, like, okay, I guess it's in complexity theory, you don't know anything, right? Every sentence has an unless P not equal to NP or something at the end. So we just
modulo all the standard conjectures. What's the right run time here?
Exactly, yes. So yes. And modulo these conjectures, what we know is that it is 2 to the omega of n to the 1/4. That's exactly what I've shown you before. I'm going to go through it like maybe very quickly. Let me tell you why. Well, because this roadmap, right? What we said is you always have to construct sets which are in a polynomial universe. And turns out what you can achieve is you can achieve n squared here, and O of that, of course, and O of n there. So you really blow up the size from n to n to the 4. This is why you get the 2 to the n to the 1/4 lower bound at the end. And we believe that this can be lowered to O of n if you cheat a little bit. But still the size from the beginning to the end blows up by from n to n squared. So really what you would get if this works out is you would get a lower bound of the form 2 to the omega of root n. Now, I don't believe that this is the right answer. I think the answer should be closer to 2 to the n. So we have to still, what I really would like to do is improve the reduction further so there's no polynomial overhead, which involves improving this first step. Okay, and here's the open question now. Recall that in these construction, in the very first step, we always had these shifts, right? These shifts which satisfy maybe they're no 3-term progressions or something close to that. Or maybe there are none of these 6-term equations. Now, it turns out you can actually do it just with 4-term equations. So this becomes Sidon sets, basically. But what we need is something slightly better than this. And this is what I would call an interpolation between 3 AP free sets and Sidon sets. By the way, is it Sidon or Sidon, or how do you actually say that? I always wondered.
I always say Sidon set.
Sit on. Okay,
And
sit
I
on.
think Erdős would say sumset.
Good. Okay, sit on. Okay, here's the question. Let G be a subset of, n squared. Maybe let's think about it as like a graph with self-loops possibly. I want to define n of G to be the smallest integer such that you can find numbers x1 through xn between 0 and that integer n, satisfying this property. So basically, I want you to attach numbers to the nodes of this graph, satisfying this property. And this property says that for every edge in the graph, ij, and for every other pair of nodes, k and l, whenever you satisfy this equality, you do it trivially. Okay.
No,
Now-
I'm sorry. How is this different from just a sit-on set?
Good. For this, you would require that it's for all ij, not only the ones in the graph. It is the same if you take the complete graph.
So this is the same restriction as for sit-on sets, except that for some tuplets, you don't care.
Exactly. For some
Sort of
tuplets, I don't care.
You're sort of relaxing the requirement by saying for some tuplets, I don't mind if
Right.
things add up the wrong way. Okay.
Exactly. That's exactly what I'm doing.
The graph encodes where you care and where you don't.
Exactly. And if you take the complete graph, you just get sit-on sets back. At the other extreme, if you take the graph where you have no
You're
edges
just
at all,
forbidding three tuples, yes.
yes, exactly. So let's take as another extreme. Let's take the graph.
Loops. AI plus AJ
Loops.
equals 2AK, yes.
Exactly. The self loops, you just forbid the tuples, then you get the 3 AP free sets. So in particular, you get that this n can be almost linear, let's say. Now, what I care about in this reduction is none of these extreme cases, but something which is pretty close to just self loops, or let's say a pretty sparse graph. The graph I care about is I want to bound n of g when g is a graph with constant degree. So it's not just self loops, it's not just a single edge per node, but let's say 3 edges per node. Can you get an upper bound on the size of these sets? I really don't know.
Kevin should hear this question, I think. Kevin O'Brien.
He's on an airplane to Miami at the moment, so
We
he
can pass it on
apologize to
to
me for the fact that he was going to have to miss the talk.
we can pass this on to him. Definitely.
Yeah, sounds great. Please do. Yeah, I mean, like let's say I haven't checked all the details again, but my strong feeling is that if you manage to show that this is linear, then you also get the best reduction which you could hope for. Meaning, like, I guess like you cannot get O of n because you will not be able to beat this bound. But at the very least, you would get something which is very, very close to a 2 to the n lower bound. It would be something like a 2 to the n to the 1 minus little o of 1 lower bound, which I think might be close to the correct answer here. Okay, yeah, so that's really it. Hopefully this question excites some of you, or okay, Kevin. Thanks.
I mean, the questions about x equal a plus b or x equal to an h-fold sumset for any h3 or greater, they're like natural questions to ask. But I'm curious, is there anything in the world of complexity where you deal with infinite sets? So does it make any sense even to ask if you have an infinite set of positive integers and non-negative integers? Can you write, is it a sumset? Or is that just nothing that in complexity you consider, because there's nothing like bounding, there's no like exponential time algorithm that deals with it.
I mean, the notion of time does make sense when you have infinite size objects in some sense, right? I cannot think of a single application where, thanks, where this is. I cannot think of a single application where infinite sets really are interesting.
And I mean, this is like a dumb question, if you like, but what does this have to do with computer science? In fact, you might ask, what does anything in complexity have to do with computer science? I mean, in computer science, you have guys trying to write programs that run fast. But, you know, knowing whether something is polynomial time in principle doesn't let you write a better program.
I absolutely agree. Okay,
But
so
you're not
my answer to
supposed
this,
to say that's dumb and, you know, this is why.
no. I completely agree with you. Complexity theory is like, okay, it's just not computer science. I think it's math, basically. Maybe not everyone agrees there, but at least it should be. Yeah. There's other aspects of computer science which are closer to real life, let's say. And I would say fine-grained complexity, which we talked about
Okay.
before, right?
Can you shut
Is
your
like,
screen share so it's easier
oh,
to
sure,
see? Yeah, thank
sure.
you.
No worries. Right. So my answer would be there's other aspects, like for instance, fine-grained complexity, which is like instead of just saying something's polynomial time or exponential time or something, you really want to nail down the
Right,
exact
sure.
complexity of problems. This has applications, right? Because it actually there has been some cases for problems, let's say in bioinformatics or something, which couldn't be solved faster for ages. And now in theory, people came along and proved, well, you cannot unless some complexity assumptions fail. So maybe this you could view as like a bridge of computer science and math, but still it's also part of math. So yeah, I don't think we don't even want to be like applicable to real world necessarily, you know, just has to be interesting. At least that's my view.
Other questions for Nick? So I noticed when I finally realized that you were in computer science on archive and not math, that you also, with some of your colleagues, have something about what's it, threesome?
Right.
Yeah. So what did you do with that? I mean, just quickly,
So from a very, like I mentioned before, right? Threesome is actually one of my favorite problems. So from a very, very high level point of view.
Right. So this is the question. If you have a set of integers, can you solve the equation a plus b equals c inside the set? That's the question.
And this is an interesting question for the following reason. You can solve this problem in, let's say, n squared time. You just enumerate all pairs a and b and test if a plus b is also in the set. But we suspect that this is the fastest you can do. And now this hypothesis that threesome requires quadratic running time became a complexity assumption in itself. And now you have proven for a lot of other problems that they cannot be solved faster than, say, quadratic time, unless this hypothesis is false. So threesome became a new hypothesis in complexity theory, similar to p is not equal to np. Now, what we did in this paper, which is also some like using some tools from additive combinatorics, like basic stuff, VSG theorem and some Ruta calculus stuff, basically is to say that whenever you start from threesome, you can assume that the set is random. Like you can just like intuitively assume it's like a uniformly random set from numbers between 0 and n cubed or something. And with constant probability, there is a solution or there's no solution. And if you can assume this, you can prove stronger reductions, basically. Like this helps you. And the way to get there is to say, well, suppose otherwise you would be structured, let's say additively structured, in the sense that maybe you have large additive energy or you have like sub-progressions or something. Then you should be able to find them, take them out, and solve it faster on these structured sets. And thereby like making the set more and more and more random in the sense. From a very high level point of view, that's what's going on there. So that's what I meant before. Additive combinatorics is really exciting for computer science right now, I would claim. Or, yeah.
And on your sumset is NP complete. I know you use sit-on sets, but it's sort of I mean, it wouldn't help you in any way or improve your results in any way if you had denser and denser sit-on sets. It's just basically the system.
No, I think it would help. Like, I mean, it wouldn't give you, like, it's still NP complete. That doesn't matter. But it would give you better quantitative bounds, assuming like, it would give you the better bound of the true complexity of the problem, assuming now the exponential time hypothesis.
Yeah. So every time someone comes up with a new construction of sit-on sets, you can plug it into your paper and slightly improve the exponent somewhere.
Sure. Okay. Though, I mean, this is only by a constant, right? I mean, sit-on sets can never be denser than like
right.
Right. So there's no way around it. So this really what I was asking the open question is, can you get considerably denser if you forget about some pairs, right?
Right.
That's what we really need. But I guess the constant and the exponent doesn't matter at this point. So yeah. There any hope, by the way, sorry, that now that I have you, like one question I was wondering, and that figured probably it's completely hopeless, but is there any hope that at some point you get a classification of all sit-on sets?
Of sit-on sets?
Yeah. Let's say all dense ones.
Well, let's say no, because we know so little about them to begin with. And yeah, you know, I
Okay.
mean, isn't
Yeah, I
it?
figured.
I mean, Kevin O'Brien is the guy who wrote the massive survey paper on sit-on sets, but
I saw.
um, you know, it's usually some guy, you know, comes up with some clever new idea, and then you have some more sit-on sets, and then the next guy comes up with a different clever idea, and you have some different sit-on sets. And it would be nice to have a theory or a pattern, if you like, or maybe it's nicer if you don't, right? Because there's no reason why the world should be regular. But
Really?
I mean,
Interesting.
yeah, yeah, I don't know. I don't know. I mean, truthfully, until I saw your paper, I would have thought that maybe it wasn't so hard to look at a set and be able to decompose it into as a subset if it were possible. So, you know, what you did suggests that it's not, but or proves that it's not, if you like. But if I were to ask you, why is sumset recognition NP complete? Is there one of the, like, standing on one leg or one foot? Could you say why? And saying, well, you can reduce 3-sat to it. So that's not an answer. That's like the proof, right?
Sure.
I mean, at odd times I've listened to people give, you know, proofs of, like, I just saw something which I'm completely incapable of understanding, because there seems to be some computer game called Super Mario Brothers, which I've never seen, but you know, it's like one of these things which is in the ether. You know the words, and someone proved that that's NP complete because you can
Right.
reduce 3-sat to that. So, I mean, you know, so like this, I mean, it makes no sense to me why. I mean, but it's just like sort of like there's this business of, you know, you try to reduce one thing to another, and you know, and it seems practically everything in the universe is NP complete. But
I mean, I can offer like a very, very vague intuition, but it's not a good one necessarily. But like the reason why these problems really are NP hard really is because you can encode an exponential search space into them. Like an exponential search space which you cannot,
right.
like, which is only locally constrained in a sense. Now, this is of course extremely abstract, and there are even some problems which have like an exponential search space and which you can solve in polynomial time. But like this notion of you can use an exponential search space and these local constraints, this is really something which all of them share. And this is something which I guess you can also see for sumsets, right? You obviously have an exponential search space, and you can encode constraints of a form that, you know, like if you have, suppose you have a hole in your set, then clearly you have a choice to make. You cannot put this element and this element because they would add up to the whole, right? So from a very, very high level point of view, it looks similar, but it's not a satisfying answer.
Wait a minute. I grew up with the belief you have all these problems that you can certainly solve by looking at all possibilities, whether it's factoring a number into a product of primes or whatever. And the only reason that we can't do it faster is because individually we're stupid. We're just not smart enough to do it. And then, you know, you guys come along and start proving, well, it just can't be done. But I always had the assumption that we were just not smart enough.
Well, you might still be right? I mean, no one is able to prove NP not equal to NP, so you might be right in the end. But
Yeah.
like, let's say at least now it's less likely.
Evidently, yeah.
I wanted to speak up and say something in
I know.
defense of our profession here, and especially results like Super Mario is NP complete or NP hard.
But when
And
you say our profession, which profession are you referring to?
theoretical computer scientists.
Oh, okay.
Uh,
I thought
in
you were a
particular,
mathematician.
well, I'm both. So, I mean, uh, you can be American and Canadian at the same time. Anyway, I think that results like Super Mario and also similar results like Go is, generalized Go is p-space hard and generalized chess is p-space hard. All these actually reveal something kind of important. Namely, why is it that some games are easy to play and other games are hard to play? And, why is it that the 15 puzzle where you have to move these numbers around in a square. Why are puzzles like that easy, but things like Super Mario and chess and Go, why are they hard? And I think even though they are specific instances of a much larger class of problems, that it reveals that deep in the structure of the rules, there's something really making it hard, whereas for other things there isn't this thing. So I think it actually reveals a really deep and interesting truth.
No, I agree. I agree.
Mm, mm. That's all.
No, I just
That makes sense.
have an emotional connection to the erroneous statement of David Hilbert that if you think hard enough, you can solve any problem. That's all. It just.
But I mean, solving it doesn't mean giving an algorithm necessarily, right? Solving
Right,
can
yeah.
also mean proving a lower
Right.
bound.
I mean, proving a problem's unsolvable is solving the problem, but it's
Exactly.
Also, you can just say like it's easier. Like now we know on which problem it's like hard. Like which problem we want to like think hard enough first. Like if we know that something is like reduced from a specific problem, we know okay, let's try to solve this problem first, and then if we succeed, we can move to the other problem.
Yeah, that's actually a very, very important point of view from like fine-grained complexity, where we just make up a bunch of assumptions. No one really knows whether they're true or not. Now, is that a good idea? We shouldn't believe anything just someone writes in the paper, right? But these assumptions do have a purpose, and that whenever you prove hardness under some new assumption, it means you shouldn't focus on that problem. You should focus on the assumption first. And it gives us a clarity of what to focus on. Yeah, it's a very good point, Ron.
other questions, comments, stories. Thank you, Nick.
Yeah,
thank you,
thank you.
Ron.
Really appreciate it.
I wish everybody who's on this side of the Atlantic a happy Thanksgiving. We don't meet next week, but we'll be back in 2 weeks, I guess. Yeah. Oh, sorry. Is this a question in complexity? Yeah, so everyone else can ignore this. This is just literally something I'm working on at the moment. So if you have a set of k integers and you look at the twofold sum set, you get a set of integers with between 2k minus 1 and k plus 1 choose 2 elements. And in fact, for every integer between those lower and upper bounds, there's a subset with that size. Okay, that's a little baby theorem, right?
Mm-hmm.
Now, if you take a set of k integers and you look at, let's say, threefold sums or h-fold sums for some h strictly bigger than 2, again, there's like a lower bound, which is like, hk minus k plus 1. And there's an upper bound, which is something like h plus k minus 1 choose 8. There's like an upper bound. But if you look at all sets of k integers, and you look at all their h-fold sums and their sizes, you don't get everything between the upper and lower bounds. There's some holes. You can prove it. Okay? That is, there's a theorem that says, like, a certain number will never appear. So you can say, okay, but I would like to know what does appear. So in this interval, what are the numbers which are the sizes of h-fold sumsets of a set of size k? So there's a way to solve the problem. Namely, you look at every set of size k, and you can put some bounds on it, so it's a finite calculation. But it's big, right? As you guys
Sure.
say, it's, it's big. And is that the kind of problem that might be not solvable in polynomial time and polynomial in the k or the h? Is there any way a priori to know whether the fact that I'm running a little computer program to for small values of h and k to see what numbers I get, which is done in, it's a little loop, you just, so it takes time. Whether if I were smart enough, I could write a better program that would run a lot faster. Oh, that's an application of complexity theory, yeah.
Sure, yeah. It's an interesting question. It's a little bit funny from our perspective, I would say, because there's no real instance of your problem, right? The instance would
no
just
real
be
what?
There's no real instance. Like the input is just a number, whatever, like is like I guess you give me like h and you ask whether k can be obtained or
No. I give you
subset.
I'm interested in if I have a set of k integers and I look at the, let's say, threefold sums.
Right.
So a plus b plus c, as they run through the elements of the set, I look at all the sizes of the sum set, and it falls in a certain interval. But
Yes.
I know there are going to be some gaps. Not every number in that interval will come up.
Right.
So
Right.
I'd
I
like
understood.
to know what is the answer? What is the set?
Then the instance of your problem would be paraphrased slightly, right? Would be to say you give me h and you give me some value s, and you ask, is there a set A such that a plus a has like h
Right.
fold has
Yeah.
size s, right?
Yeah,
So
exactly.
the input problem you've given me is h and s, which is just two numbers.
Right.
So there's no real instance to begin with, like no like large instance, just two numbers. And I would say we don't really have a lot of problems for which this is like a hard problem. I mean, this goes into the same as like detecting whether a number is prime or something. These are some instances for which we cannot really make progress on proving that these problems are hard. It is possible though. As per you, the specific problem, I have no idea.
Right.
Is it something you would actually want to have like a computer program for?
No, I want to have the answer.
Okay, interesting.
I don't care about a computer program. I want to know, like I'm still trying to solve the problem for h equals 3 in different sets k. So
Yeah, it's an interesting question.
I was surprised that I could prove there were gaps.
Uh-huh.
And but then I'm like, well, what are all the gaps? I don't know. I mean, I haven't been clever enough to figure it out, and I can run a little. My program is trivial. I write my programs in Maple, but it doesn't matter. It's still a program. It still runs.
Sure.
But
Interesting.
But I don't know. I guess my question is, there are all these questions one can ask in additive combinatorial number theory and other parts of number theory, and for any one of them, one could ask, how hard is the problem from the point of view of complexity theory? I guess that's really the thing.
I agree. I think, like from our point of view, we don't really know exactly what would be extremely interesting. I guess, I think for this specific problem, a lot of people, let's say, two papers have asked this question before, and we're hoping that by getting a faster algorithm, you understand some structure of sumsets. Now, it turns out that probably will not happen. I guess there should be some gain for the other problems as well, other than just saying, well, it's an interesting question to begin with. So if you have some specific examples for which for which you have some hope that like a computational perspective would give you some insight, then they would be even more interesting. But I think in any case, when you find these problems, please, forward them to us. Maybe specifically Ron, who I think in his PhD is extremely excited about this.
If you're free at this time, 2 weeks from today, that's my talk in this seminar. So
sure, yeah, I'll be there. Sounds great.
And If I can write it down in advance, I'll send it to you so you can give me
Sounds
the
good.
answers right away. You can say before you even start, here's the answer to your question, and oh, thank you. Go have lunch now.
Nah, let's not do that. But okay, sounds great. Yeah.
Okay. All right, all. Thank
Thanks.
you very much. See you
Yeah, thank
perhaps
you.
in 2
Appreciate it.
weeks.
Happy Thanksgiving. Well, you will.
Thank you. You too.
Bye bye.
Be well, David.
Bye.
Bye bye. Happy Thanksgiving.